Welcome to the first day of Virtual DAC 2020. I have to admit, I'm much happier this year attending sessions in my home office, much cooler than last year in Las Vegas. Although, I did win some extra spending money at the casinos last year. Before I introduce our General Chair, Zwali, there are a few reminders for the Monday program. First, today is Tutorial Monday. There are 12 technical tutorials starting after the keynote. If you have a full conference badge, please check out the tutorials, and remember, if you find more than one you want to attend, you can attend all sessions on demand through August 1st. We have 3 outstanding sessions today, which every attendee can experience. Under the Tech Talk and SKYtalk tab, you will find the following sessions. Remember, save sessions to your virtual DAC agenda and revisit them later in the week. Exhibits are open for live discussion today from 10:30 to 1:30. There are over 60 exhibitors, and their virtual exhibits are looking awesome. There are videos to watch, content to review, and staffers to meet. The Design on Cloud Theater presentations also start today at 10:30. You can find the schedule under the Exhibits tab on the homepage. What's that, 5G? Oh, how can I forget to mention the best of DAC? Today, we will also have the IEEE, ACM, and DAC awards. You can view videos from the award presenters and recipients. There will also be a meet and greet the award winners at 5:30 today. Check them out and congratulate the best that DAC has to offer. And what's a conference without mingling with colleagues and happy hours? Join your friends and colleagues starting at 6 p.m. for DAC Trivia, or Wine About Verification with Brian Bailey, or join the General Chair and chat about your first day at DAC. These are happy hours, so bring your favorite beverage. Now, let me introduce the 57th Design Automation Conference General Chair, Zwali.
Thank you, Debbie Dac. Ladies and gents, this is the moment you waited for. Welcome to 57 Design Automation Conference, which is also the first virtual DAC. For every great show, there's a great team behind it. These are faces behind the DAC 2020. Working with this amazing group of experts from academic and industry, along with MP Associates, Howard Erickson, and sponsor representative from IEEE and ACM, plus hundreds of volunteers, such as TDC members, tutorial organizers, session and panel chairs. We're here to present DAC 2020 for all of you. No matter where you are and when it is right now, we hope you enjoy the greatest show of our industry. At this moment, I'd like to thank our industry sponsors again for your great support. Generally, next part will be the award ceremony. But this year, due to the virtual DAC, we're going to do a little bit differently. You're going to find a dedicated award page on the DAC virtual platform. There, you will find the award chairs from IEEE, ACM, and DAC to announce those awards. Something new this year, you're going to hear the video clips from all the award winners who may share a little bit of their own story, and that'll be fun to watch. We're also going to have interactive sessions this afternoon and also Friday afternoon, so for the attendees to have a chance to interact with them. Please also remember, every afternoon we're going to have a virtual happy hour and a networking event. Just like a traditional physical DAC, please bring your favorite drink with you. Our industry came to the big success today with the contribution and help from many, many great people. I would like to take this moment to pay tribute to some members of our community who passed away in 2019 and 2020. They contributed to this industry, to this conference, and to technology who help form where we are today. They are Ian Burgess, Albert Cross, Bing Liu, Donald Lucas, and Randy Smith. Pramod Subramanian. It is also sad to notify everyone, we just learned last Wednesday that Pat Pistilli passed away. Pat and a group of pioneers in our area helped found the first design automation workshop 57 years ago, who became DAC today, and also served as the first DAC chair. He later founded MP Associates, who became the conference management company for the DAC. Let us take this moment to pay tribute to all of them now. DAC 2020 see amazing growth in all submission areas, from research to design, IP, and embedded track. On the research side alone, we see amazing 20% increase in the submissions. Out of 984 submissions, we have 228 papers accepted. On the machine learning, AI, system, and architecture category, not to be a surprise, we have about a 210% increase. But more importantly, we see healthy increase in all the DAC themes, such as the design, embedded systems and software, autonomous systems, IP, security, and of course, our foundation, traditional EDA. That's quite amazing. Two contests also happen with DAC together, a system design contest and Hack at DAC. You'll find more details at the two special designer track sessions on Monday and Thursday afternoon. Last but not least, we still provide the exhibits at Virtual DAC this year. More than 60 companies, including Cadence Design Systems, Mentors of Things Business, and Synopsys, plus many other amazing companies, will be showcasing their latest technology advancement in electronic design industry through the live session and Zoom video sessions. Now, it is my great pleasure to introduce today's keynote speaker, Dr. Philip Wong. I first met Philip about, I think, 7 years ago at a local Texas workshop, which I learned a lot from his talk. Dr. Wong right now is a Willard R. Inez Kell-Bell professor at the School of Engineering, Stanford University. Since 2018, he was on leave from Stanford University and joined TSMC as corporate vice president. Since 2020, he has been the chief scientist at TSMC. Philip joined Stanford as a professor back in 2004, and before that, he was with IBM T.J. Watson Research Center for 16 years. He is an IEEE fellow. He received the prestigious award from IEEE Electron Device Society, the J.J. Alberts Award. He has been the guest editor, community chair, and general chair of many prestigious journals and conferences. He and his students won Best Paper Awards at premier conferences such as ICC and Symposium of Wilson. He has received an honorary doctorate at Polytechnique de Grenoble, France. He is the founding co-director of Stanford Non-Volatile Memory Technology Research Initiative. He is also the faculty founding co-director of the Stanford SystemX Alliance, which is an affiliation program of focused on the building the systems. So as you can see, Philip has rich experience from both academia and industry. This gives him a unique view of both at a device level and also system level. Today, he's going to share his personal thoughts on the advances of the semiconductor technology from a system perspective. I think that matches perfectly with the DAC theme. From chips to systems, we learn today and we create tomorrow. With that, let's welcome Dr. Philip Wong.
Good morning. I am Philip Wong from Stanford University and TSMC. This morning, my colleague at TSMC, Karen Akabada, and I will speak on a system perspective of semiconductor technology going forward. Future electronic systems will continue to rely on and increasingly benefit from the advances in semiconductor technology as they have had for more than 5 decades. Semiconductor technology plays a truly vital role for humanity, not only in terms of economic development, but also in the way we live, the way we work, and the way we enjoy life. This vital role has been literally exemplified today by the deployment of high-performance computing to study coronavirus protein docking in order to find a cure for the infection. 21st century applications are going to be data-centric. Data analytics and machine learning applications are going to dominate, from data center to mobile and IoT, from collecting, processing, to curating the data to derive information. Many systems will need to learn and adapt on the fly. For this talk, I'm going to focus on technology trends that have these applications in mind, namely data analytics, machine learning, and AI. And that means I'm going to focus my attentions and discussions on systems such as GPU and accelerators, and not on the mainstays of the last century, the CPU. For these applications, a key bottleneck is data movement. Energy consumption for data movement is the problem to solve today because data movement is expensive both in terms of energy and latency. The data here are measurements from a conventional system. Configuration is listed at the bottom of the slide, made by my colleague at Stanford, Professor Subhashis Mitra. A vast majority of the energy consumed is in the memory access. This includes energy consumed by the memory, as well as energy consumed by the compute while waiting for data from the off-chip memory. Computing speed and energy efficiency for abundant data applications are limited by connectivity to memory. Many recent application workloads, including deep learning, which is shown on this slide, are dominated by access to memories. Caching becomes less and less effective for these computing workloads. As a result, the majority of the energy consumption is wasted in data access, and a small portion is consumed by the compute circuitry. While this may be a challenge, it is also an opportunity for massive gains if we can focus on developing technologies with system performance in mind. With this in mind, let us look at what semiconductor technology has provided us in the past few decades and make some projections into the future. So far, advances in semiconductor technology has been driven by two-dimensional scaling. If you look at the density of transistors, logic gates, and on-chip memory, no matter whether it is the number of transistors in a microprocessor per unit area, the logic gate density, SRAM density, or simply the density of the inverter in a standard cell layout. Whatever your definition for density is, you see that the density has been increasing exponentially, even today. And 2D scaling is the technology driver. However, if you look back in history, advances in semiconductor technology has never been sustained using just one method. The success of 2D scaling, or Moore's law, has been sustained by a variety of innovations. In the beginning, there is the not scaling. That simple theory, which all professors teach in BOSI design and device technology classes, I certainly do that at Stanford for my EE316 class on BLSI devices, provides that as transistors are scaled down in size, they become faster and more energy efficient. But the industry has departed from the not scaling long time ago. Yet, semiconductor technology has continued to progress, although not in exactly the same way the not scaling prescribed. After the not scaling, there came equivalent scaling brought on by strained silicon and high-K metal gate. Then the concept of using channel geometry to control charge channel effect brought us FinFET. Now, much of the density gains come from design technology co-optimization, known as DTCO. This is Exhibit A that shows that when one knob has reached diminishing return, there are many other knobs available. There are many roads that lead to Rome. Semiconductor technology is a history of innovations that have provided continuous benefits generations after generations of technology products. And we have achieved these goals via different means. The semiconductor industry has already made several important shifts in the past. When Gordon Moore wrote the famous Moore's Law paper, Bob the Knot's scaling rule was not even invented. Then the knot scaling slowed down, and we switched to equivalent scaling through strained silicon and high-K metal gate. When the planar transistor reached limitations, we went 3D in the transistor structure and brought in FinFET. And today, there is DTCO, design technology co-optimization, which continue their density scaling path. When one method begins to saturate, there are multiple other knobs waiting in the wings. One of the most important attributes of 2D scaling is that it gives us more transistors per chip, resulting in cost reduction and other system benefits. Let me illustrate the benefits of device density with a thought experiment. In this thought experiment, imagine having a transistor with performance but without density. On the left is a chip with high device density, and on the right is a chip with low device density but transistors with high performance such as speed, energy, and power efficiency, and so on. For the chip on the right, even though the transistors themselves may have good performance, the overall chip and the overall system that is supported by the chip are still not useful because without density, the number of devices available will be small. As a result, there would not be enough memory or cache. There will be no multi-core chips since it requires more transistors to implement multiple cores. There will be no accelerators for the same reason. And because the devices are spaced far from each other, the long wires slow down chips and they consume far more energy than chips that have transistors close to one another. Let us look at abundant data computing in particular. Here in this graphic shows system throughput on the y-axis and range of tasks that can be executed on the x-axis. The CPU can execute a variety of tasks and has been the mainstay for computing. The emergence of abundant data computing, or data-centric computing, created an opportunity to further optimize the system throughput by trading off this flexibility to gain system throughput and energy efficiency. Data-centric computing favors domain-specific architectures, or DSAs, such as the GPU, the TPU, and similar accelerators that are able to execute a narrow set of tasks in a massively parallel fashion with high speed and high energy efficiency. A recent paper from NVIDIA, Stanford, UC Santa Cruz, and MIT highlighted 4 sources of acceleration for modern-day GPU and accelerators. Number 1, data specialization. For example, specialized logic to perform an inner loop function. Number 2, parallelism. Parallel units that exploit locality and make very few global memory references. Number 3, local and optimized memory, storing key data structures in many small local memories. Number 4, reduced overhead, specialized hardware to reduce the overhead of program interpretation. All these rely on having large number of transistors to support them in a specialized way. In other words, modern architectures are using large number of transistors to gain performance and energy efficiency. As an example, the GPU peak throughput has a strong correlation with the transistor count of the chip, as shown in these data from GPU products. I will come back to this point later in this talk. Device technologists such as myself like to talk about oxide thickness, gate length, mobility, contact gate pitch, minimum metal pitch, and such. These are very important and necessary, but more and more we find that is not enough. Today, we need to take a top-down approach. Application drives design choices, and design choices are informed by system technology options. And there needs to be innovations up and down the system stack to arrive at the best solution. It is like a Jenga game. If you pull out some pieces in the middle or the bottom, no matter how good the top layer looks, the stack is going to fall. First, let's look at evaluating performance from system perspective using the ROOFLINE model. The ROOFLINE plot visualizes attainable performance limits imposed by processor efficiency and memory access on a single graph. Ideally, processor peak throughput and memory bandwidth should improve simultaneously such that the flat and the slanted portions of the roofline can be lifted up in parallel. The processor peak throughput is the product of number of cores, the core frequency, and the number of operations per cycle. The memory bandwidth is the product of the bus width, the bus frequency, and the data rate. The core frequency and bus frequency are no longer efficient knobs to drive the growth due to limitations by thermal design power and or power density. The number of operations per cycle and the data rate depend on the tasks at hand and the architectural design and industry standards. Architectural tricks such as these have limited room for improvement. The key area for growth for processor peak throughput is the number of cores, by introducing even more parallelism. And for the memory bandwidth, the bus width has the most potential to grow because the technology to do so is ready. And I will elaborate on this later. These opportunities point to an important observation. We need more transistors, more memory, and more connections between transistors and memory, combined in a package to improve system throughput. In the coming slides, I will illustrate these points based on the server and data center GPU trends related to throughput and bandwidth. Peak throughput has advanced by 1.8 times over a 2-year cadence since 2007. That peak throughput increase is mostly due to multiple cores. While clock frequency is an important performance indicator for CPUs, for abundant data applications such as data analytics and AI that uses GPUs and accelerators, throughput is a strong function of the core count, close to a 1-to-1 correlation today. And because the transistor count per core has remained roughly the same, the peak throughput is a strong function of the number of transistors on the chip. One can also arrive at the same conclusion by noting that the peak throughput is directly correlated with the number of transistors on this chip. What really happened was that key application focus has changed from CPU dominated to GPU and accelerator dominated. And with that change, semiconductor device technology has found a new domain for performance growth by offering more transistors. And these transistors are provided at a cost that is acceptable for the targeted end product applications. Otherwise, there would not have been any end product offered during the last 2 decades. Of course, we also need advances in multi-core architecture to go along with this solution. The point I want to make is no one abstraction layer alone can solve all the problems. The transistor count is driven mostly by transistor density increase at about 1.6x every 2 years, with a small contribution from die area increase. Note that the digital portion of the chip increases at a faster rate than is shown on this plot because there are other parts of the chip that scale slower than the digital part, such as analog and I/O. So let's talk about transistor density and transistor count. Transistor density, shown by the blue data points here, continues to grow at about 1.84 times on a 2-year cadence for CPU. This is for data from whole chip. So again, the raw digital transistor density growth is even larger as the whole chip includes I/O and other non-scalable parts. There is a long-term trend, and there is also the latest trend up to 2020. So for those who claim transistor density is not improving, I suggest you look at the actual data. The trend has not changed in the last decade. Of course, this does not mean gate length, contactor gate pitch, or minimum metal pitch, and as such, low-level metrics have been shrinking at that same rate. For example, the density represented by 1 over the product of the contactor gate pitch and minimum metal pitch, shown by the red data points here, has been growing at only 1.69x on a 2-year cadence. What has happened is that DTCO, design technology co-optimization, accounted for much of the density improvements in the last decade. And this has not been properly captured by conventional metrics such as contactor gate pitch and minimum metal pitch and other similar low-level metrics. We believe this transistor count trend will continue for quite a while. Some will come from continued 2D scaling, and some will come from 3D integration, some will come from DTCO, some will come from larger dies. Here are some examples of how DTCO contributes to logic density. Dimensions such as contactor gate pitch, minimum metal pitch, and fin pitch do depend on dimensional shrink. However, more and more, we observe that reducing the number of tracks in standard cell layout design and innovative knobs such as single diffusion brick and contact over active gate allowed us to maintain the historical device density growth trend. Of course, all these logic computations require data from memory, as shown in this transistor count versus memory capacity plot. There is close to 1-to-1 correlation between the number of transistors and the amount of memory for all computing systems, from mobile to desktop to servers, and even the largest supercomputers in the world. A correlation over 8 orders of magnitude is quite amazing. Memory is plentiful, at least those that are off the logic chip. So for now, we will make the assumption that memory capacity is not a limiting factor, but we should always keep in mind to make sure that this assumption is satisfied. We will come back to the question of memory later, as this is one of the most exciting areas of technology development that can make a real difference in the way we architect the computer. All the memory is sitting outside the computing logic is useless unless the logic can access the memory. Next, I want to talk about memory bandwidth. The bandwidth is simply the data rate times the bus frequency times the number of I/O, or bus width in bytes. The bus frequency, similar to the processor clock frequency, grows at the expense of added power. The bus frequency can improve the bandwidth, but only at the expense of more power. The power-friendly knob is the I/O count and, more specifically, the bit width per memory channel. The peak bandwidth grows at about 1.56 times every 2 years. This is slower than a peak throughput growth rate of 1.8 times per 2 years for logic. Thus, there is a bandwidth deficit, and this limits the system throughput. In an earlier paper, Professor David Patterson wrote, if everything improves at the same rate, then nothing really changes. When rates vary, we see real dislocation that in turn requires real innovation. The imbalance requires innovation. To increase bandwidth and bandwidth per watt, the most important and effective knob is to increase the I/O count. Fortunately, there's a lot of room for the I/O count to grow, and this requires innovations in compute memory integration. Let us take a step back and look at the various ways of compute memory integration. Here is a traditional two-dimensional system or 2D system, which I call the baseline for comparison. There are off-chip DRAM chips in a DIMM socket on a printed circuit board, connected to the silicon logic die by fairly limited number of I/Os. One step ahead, there is a 2.5D system where HBM-type DRAM are stacked by through-silicon via, or TSV, and connected with the silicon logic die by an interposer. The interposer has connectivity on the order of a few tens of micron pitch and has more I/O than the 2D system I showed earlier. One can go one step further and imagine stacking the HBM-type DRAM on top of the silicon logic die. With through-silicon vias or TSVs and microbumps, we can get micron-scale connectivity that ties memory and logic on a single 3D chip. TSV pitch can go down to single-digit micron scale. Much finer grain and denser connectivity can be obtained by monolithic 3D integration, which we call next system. The 3 stands for 3D. And I believe this is the kind of system you will see in the future. The vision is to have multiple layers of logic and memory. The memory layers span the gamut of high-speed memory to high-capacity memory. The high-capacity memory can be in 3D to achieve high density, as shown in here with the green blocks. Here is an example of next nanosystem. As mentioned before, there needs to be a large number of logic transistors on chip. At the same time, there needs to be a balance between logic and memory on this 3D chip. Otherwise, memory bandwidth and latency will be a bottleneck. Therefore, there needs to be multiple layers of logic and memory on the same chip. And these logic and memory layers will be finely interleaved with one another and connected with ultra-dense, fine-grained vias. Indeed, vertical interconnect density associated with advanced packaging featured about 3 to 4 orders of magnitude improvement in the last decade alone, using a variety of chip-level and wafer-level technologies. Today's most advanced TSV is about 5 to 10 micron pitch. Using wafer-on-wafer or SOIC technology, the pitch can be about a micron. And if we go monolithic, the interlevel vias or ILV can be 100 nanometer or below. So there is at least another 4 orders of magnitude to go as far as bandwidth improvement is concerned. The distinction between on-die connectivity, such as vias and on-chip interconnect wires, and off-chip connectivity, such as TSVs and microbumps, will become increasingly blurred. Wafer-level monolithic integration technologies and packaging technologies will smoothly blend into one another in the future. Monolithic 3D integration is really a continuum with 2.5D and 3D packaging. This includes both chip-level and wafer-level packaging. It is the number of connections, the density of connections, and the energy for pushing the data through the pipes that are important, not the particular way these are achieved. As you see on this plot, the connection density spans more than 7 orders of magnitude. There is at least 3 to 4 orders of magnitude of improvement to be gained, going from today's chip-on-wafer solution to tomorrow's monolithic 3D integration. Let's tie all these together. To adequately describe future semiconductor technology, one needs to take a system perspective. For abundant data applications, such as data analytics and AI, the peak throughput and the peak bandwidth are the 2 quantities that will raise the roofline in a plot of throughput and operational intensity. Shown here on this plot are roofline plots of GPU products from 2007 to 2019. Both the processor peak throughput and the peak bandwidth have been raised. However, as you can also see by the red arrow, peak throughput has been growing faster than the peak memory bandwidth, and this creates an opportunity for system improvements even at the same logic load. The roofline model shows us that 3 metrics are important for a semiconductor technology: logic density, memory density, and interconnect density between logic and memory. We call these metrics DL, DM, and DC with units of numbers per millimeter square. For example, today's publicly available data shows DL, DM, DC to be about 100 million, 200 million, and 12,000 per millimeter square, respectively. These 3 numbers will capture the most important attributes of a semiconductor technology going forward. A point of view paper as the proceedings of the IEEE published in April this year elaborates on the rationale behind. Let me summarize our discussion so far. Semiconductor technology is key to economic growth, protecting the environment, improving healthcare and education. Nations around the world have also recognized this importance for national security and technology leadership. For the past 50 years, semiconductor technology development has been akin to walking inside a tunnel. The road ahead was clear, as there was a well-defined path and everyone knew what needed to be done. Now, we are approaching the end of the tunnel. Technology gets harder to develop, yet the future now has many more possibilities beyond the tunnel, and we are no longer bound by the confines of the tunnel. Innovation and a clear-eyed vision are necessary for continued advancement of technology that is so fundamental to the 21st century society. So we have outlined several important technical directions. First, the number of transistors. This correlates with peak throughput, and we must increase this. This can be achieved by 2D scaling, DTCO, and adding 3-dimensional logic layers. Second, logic memory integration, bringing memory as close to logic as possible and increasing the I/O count between logic and memory are most important for increasing the peak bandwidth and bandwidth per watt. There are many options ranging from packaging technologies to wafer level integration. In fact, these technologies will increasingly blend into each other. So far, we have assumed the architecture would use pretty much the same logic and memory devices we have always had. But that can also change when new memory appears that enables a different architecture. Finally, this is the Design Automation Conference, and I would like to say a few words about design tools. New design tools that optimally perform system partitioning will become indispensable. System partitioning needs to be performed across dies, not just within die. Finally, perhaps most importantly, I want to talk about democratizing innovation. In an application and system-driven world, it is extremely important to have an ecosystem that fosters innovation. Today, chip design is a very expensive activity, affordable by only a small number of companies when it comes to the most advanced technologies. As a result, innovations in hardware systems are limited to a small group of engineers. This is very different from innovations in software applications that oftentimes comes from a much broader cross-section of society. If design tools and the ecosystem can lower the barrier for entry for chip design and system implementation, an enormous amount of innovations in hardware will be unleashed. We will see a renaissance of application and system design. Ideally, it should be as easy to innovate in hardware as it is to write a piece of software code. Let me illustrate this with an example. This is an example of an advanced high school college freshman hardware project. It's a Stanford EE47 class, an introductory class for building electronics at Stanford. You see the parts are rather simple. There is an on-off switch, a display, a microcontroller, a USB bus, and some LED lights. And the system does not do much. So it is not very interesting other than to those that are extremely motivated. If one day, even a high school student can design their own chips, put them in a board, and demonstrate an application in a way that is as easy to write a piece of software, then we can unleash a lot of innovations for the betterment of society. I believe this is a dream that will come true one day. I would like to thank my students who have collected some of the data shown here today. Their research has been a valuable source of inspiration. I would like to thank my longtime collaborator, Professor Subhashis Mitra, and Karen Akabada, who is a co-author of this talk, as well as Professors Dimitri Antoniadis, Jeff Bokor, Cha-Ming Hu, Soo-Jae King Liu, Jim Plummer, and Saeed Salahuddin. My academic research is supported in part by the Stanford SystemX Alliance, an industrial affiliates program focused on building systems. I wish to thank my sponsors from the SRC Jump Accent Center, the National Science Foundation, and DARPA ERI 3D SoC program, and the Stanford Non-Volatile Memory Technology Research Initiative, NMTRI. This is the end of my talk. Thank you for your time, and I'm happy to answer questions that you may have.